Hi, and welcome to week 7, day 2. Today we're going to talk about two things. One of them is the vector magnetic potential. And the other one is inductance. So let's start with the vector magnetic potential, and we'll forget about inductance for now. It is a property, all right, of the curl that for whatever vector field you want to choose, if you define some vector field and give it the name A, it's an arbitrary, if I can remember how to spell arbitrary vector field, right? Then the curl of A has 0 divergence. Cool, perhaps not really relevant to our interests, but all right, let's go with it. But here's the key thing. We also know from Gauss's law that the divergence of the magnetic flux density is 0. So that means that the magnetic flux density could be the curl of some vector field. It could be. Not saying it is, not saying it's not. It could be, though, because they both have this 0 divergence property. All right, well, let's suppose that it is. We can then define the magnetic vector potential so that our friend B, the magnetic flux density, is the curl of, we're going to name it A. That's the standard name for the magnetic vector potential. I'm not just making that up. Then, if you substitute this into Ampere's law, and you choose a value for the divergence of A. Remember, we're making this up. We have no idea what A is. And we can choose it to be whatever is convenient for us. So we're going to choose that the divergence of A is equal to 0 for this situation. Then Ampere's law becomes the Laplacian of A is equal to mu J, where J here is the current density. That's a volume current density in general. That's a new form of Ampere's law that uses A instead of B. Now, here's the convenient thing about this. An equation that is of this form is called a vector Poisson's equation. And in general, those equations all have the same form for their solution, too. So their solution is that A is equal to mu over 4 pi times the volume integral over some volume that we're going to name V prime of J of the position variables inside there divided by the position variable in there. That's the distance from the, well, let me rewrite that a little better. That would be magnitude of r minus r prime again, and we're going to turn out that a is going to be a function of r dv prime. So that's going to be a function of whatever primed variables make up r prime. So we'll write this a little bit more clearly too. A here becomes a function of r. So as usual, when you evaluate this integral, your primed variables disappear, and you're left with only things that are in terms of r. That was too dark. You're only left with things that are in terms of r. Key things to note here are that, unlike other things involving the magnetic field, the contribution to the magnetic vector potential from each differential current element, we can call that dA, right? The differential contribution. It's in the same direction. The same vector direction. As that differential current element dJ, which is really nice because the rest of the time when you're working with the magnetic field, you have to do a lot of cross products, and this eliminates all the cross products. So this form eliminates having to do any cross products in your integral for the solution. Then at the end, when you found whatever A is, the vector magnetic potential, you can get the magnetic flux density using the fact that the magnetic flux density is just the curl of A. So your life becomes a lot easier in general because you have done that. In general, this is a good replacement for figuring out the magnetic field using the Biot-Savart law in the same way as the electric scalar potential is a good substitution for doing a Coulomb's law problem. And that's pretty much all there is for the vector magnetic potential. The one other thing that I want to point out is that you can use the magnetic vector potential instead of B to find the magnetic flux through a surface. Remember that the magnetic flux through a surface is the surface integral of B dot ds. But if you use Stokes' theorem, which remember that the flux integral of the curl of some vector field A dot ds is equal to the contour integral around the boundary of that surface of A dot dl, the answer becomes clear. All you have to do to find the flux through that surface is integrate A around the boundary of the surface. As always, be careful about the direction of your surface normal vector and your contour integral differential element dl, because those things have directions and you can end up with a sign error if you don't do that. So that's kind of all there is to it. You'll find that the magnetic vector potential is even more useful when we move away from static stuff. It's the most convenient way to deal with radiation from time-varying electric currents, and we end up using it a lot for that. But that's only going to be very briefly touched on in this class, and it's more of a thing in your antennas class or in your more advanced electromagnetics electives. So that is the magnetic vector potential in a nutshell. Use it instead of the Biot-Savart law. It'll make your life easier.